Assalamualaikum warahmatullahi wabarakatuh. So this is our lab presentation and we are from group 4. So this is our group members which contains of Muhammad Syahmi bin Muhammad Zainuddin, Nik Hairul Hazril bin Hazil, Nuraliah Hanissa binti Misan and Nurfaraliyana binti Samburi. So the introduction. Modeling and dynamic stability analysis are crucial in engineering, especially in complex system application. They help engineers understand system behavior and predict its reason to disruption, leading to safer, more reliable and effective system. Our system stability analysis examines a system dynamic behavior under different conditions and disturbance, ensuring the electrical grid operates safely and reliably. Dynamic stability system examines the system for return to equilibrium, preventing cascading failures and ensuring a fast recovery process. The study focused on three main stable aspects: grid reaction to gradual change in energy, dynamic grid response to major interruption, and transient grid response to minor disturbance. For the scope, as you can see, this is figure 1.1, a simple two-area system. This system consists of two areas connected by a weak tie, each with two copper units with 900 MVN to 20 kV ratings. It includes a 4 generator and 4 transformer, each with an impedance of 010 plus 0.15J per unit. Step-up transformer plus alternating electricity voltage, reducing power loss in power line. Generator converts mechanical energy into electrical energy, powering sites not connected to the main grid or backup power blackouts. So for the objective, we have two objectives for this lab. The first one is to model a test system model of power system using MATLAB Simulink. The second objective is to analyze the dynamic responses of the system following a disturbance.
Assalamualaikum, my name is Muhammad Syahmi bin Muhammad Zainuddin. My matrix number is AE200035. So I'll be presenting for the methodology part. So in the methodology part, there is 5 points to discuss, which is power system stable theory, definition of power system stability, power system unstable theory, type of power system stability and type of disturbance, and last but not least, how to determine the critical clearing time and angle. So for the power system stable theory which is a significant part of electrical engineering, which is focusing on generating and transmitting electrical power efficiently with minimal losses. So power system stability is crucial, which is referring to the system stability to return to a steady state after disturbances. Assist systems have been the preferred choice for power generation and transmission globally since the 20th century. So for the power system stability definition is how the system handles disruptions and bounce back. It includes steady state, transient, and dynamic stability. Steady state stability checks how much load a machine can handle without losing sync. Dynamic stability also deals with small disturbances, and transient stability tackles large disruptions causing big changes quickly. And for the power system unstable theory, which is looks into how electrical grids behave, focusing on voltage, angle, and frequency changes. If left unchecked, these issues can cause blackouts. So engineers use math and control theory to find and fix the problems, which employing strategies like automated generations control and advanced technologies such as FACS and HVDC system to keep the grid stable. The aim is to understand the instability and use controls to keep the grid reliable. As for the type of power system stability and type of disturbance, there is power system stability includes transient, voltage, and frequency stability, each handling different aspect of grid operation. Transient stability deals with short-term disruptions, whilst voltage stability keeps voltage levels stable, and frequency stability maintains the consistencies of frequency after sudden changes. Disturbances also like faults, load shifts, or network adjustment can challenge grid stability. So in understanding this, how these stability types interact with disturbance is crucial for a reliable power grid. And the last one is how to determine the critical clearing time and angle. So In a power system involve using simulation software to analyze transient stability. So engineers observes how the system respond to disturbance like faults, identifying the CCT as the maximum fault clearance delay before the instability and critical clearing angle as the maximum rotor angle deviation. It's allowed without instability. Analyzing this simulation results helps pinpoint the critical condition and assess system stability, which is guiding to development of strategies to improve stability and ensure the reliable grid operation.
My name is Nurfaraliyana Saburi. My metro number DE210111. I will explain the result of disturbance caused by the sudden increment and decrement of load at bus 9. Since it relates to bus 9, I will focus on area 2 for analysis. It includes four graphs: rotor angle, rotor speed, power, and voltage over time. So for the rotor angle and rotor speed, the system become unstable condition. For the power graph, it have the system unstable at the beginning and stable around 0.2 seconds. While for the voltage graph, so it have a small spike at the beginning and start to become stable around 0.05 seconds. The system start running and after reaching 0.5 seconds, the circuit breaker will close. So for the rotor angle, the system become unstable conditions. For the rotor speed graph, the system almost to regain to the stability. While for the power graph, so it failed to maintain to the stability because the sudden increase at the 0.5 seconds, which is leading to the breakdown. For the voltage graph, initially it have the stable condition, but around between 1 to 1.2 seconds, it have the voltage spike, and then after that, it become the stable conditions. The orange switching times, the rotor angle and the power graph show the unstable condition, while the speed and voltage graph it show the stable conditions. The rotor angle graph, the system running at the unstable condition. For the rotor speeds, it almost reached the stability, but it's still in the unstable conditions. For the power graph, so it's experiencing instability and which leading to the breakdown to occur. While for the voltage graph, it have the instability temporary, but it regain to stability starting at 1.5 seconds. Therefore, the sudden large decrement is highlighted as the unstable conditions.
My name is Nuraliah Hanissa binti Mishan. I will explain about temporary bulb 3-phase fault at bus 8. So for this part, we only change the parameter at fault, which is the switching time. For the switching time value, we choose 1 and 5.5 seconds. So at the circuit breaker 1 and circuit breaker 2, the value is same, which is 1.1333. This figure shows the parameter that we use. Next, we go to the result. According to the graph, faults start to appear at 1 second. Due to the temporary fault at bus 8, the system becomes unstable until 6 seconds. So the graph also illustrates how the rotor angle and speed become unstable and increase through the fault. After a temporary fault between 1 to 6 seconds, the rotor angle speed starts to increase due to the power injected to the prime mover exceeding the power retracted from the rotor while causing the system unstable during the initial stage of the fault injections. The circuit breaker will initiate a tripping signal and stabilize the system. Nevertheless, the system begins to stabilize once again at 6 seconds when the temporary fault disappears. Next, I will explain about permanent voltage 3-phase fault at bus 8. So for this part, also same, we only change the switching time at the fault. So the value that we use is 1.5. This is show the all parameter that we use for the permanent board three-phase fault at bus X. So for the circuit breaker 1 and circuit breaker 2, we use same value, which is 1.133 seconds. Next, we go to the result. According to the graph, faults that appeared at 1.5 seconds. To detect the permanent fault at 1.5 seconds, the circuit breaker is set to 1.1333 seconds. The graph also show the rotor speed, rotor angle, and electrical power versus time, indicates that a permanent board fault can have a significant impact of the system stability. The fault at bus 8 caused the system to become unstable for a brief time of period. The graph also illustrates the variation in parameters that occur in the system during the fault, which briefly caused it to become unstable. Rotor angle and speeds become unstable and increase when the fault occurs. At 8 seconds, the system begins to stabilize once more. It is observed that the rotor speed, rotor angle, and electrical power experienced at 1.5 seconds increase due to unbalanced condition resulting from a power system fault. A permanent root three-phase fault can cause significant change in the rotor speeds, rotor angle, and electrical power of the machine over time, thus affecting transient stability. This refers to the response to the large disturbance that can cause significant change in rotor speed, power angle, and power transfer. And lastly, it shows that the circuit breaker can trigger the trip signal during the fault may be used by the system to accommodate the fault state. Lastly, I will explain about critical clearing time (CCT) and critical clearing angle (CCA). So for this part, we use the data and the result for temporary and permanent both three-phase fault at bus 8. The longest period of time allowed to eliminate a disturbance without affecting system functionality is known as a critical clearing time (CCT). System stability will be ensured if the disturbance is resolved before the time limit. Nevertheless, the maximum amount of time allowed for disruptions cannot be exceeded if the system becomes unstable. The power systems simulation graph for temporary and permanent both three-phase fault on bus X differ as shown in this figure. Removing the fault required a maximum of 5.5 seconds according to the temporary both three-phase graph that contains four graphs, which is rotor angle, rotor speed, electrical machine power, and voltage magnitudes. The system regains stability around 5.5 seconds. The system is stable again. The problem was resolved before the designated times. In the graph for permanent both three-phase, the fault occurred at 1.5 seconds. Upon reaching the maximum time (CCT), all four graphs return to stable states. So when a problem is clear without losing synchronization, the maximum change in the load angle curve is referred to as the critical clearing angle, which is CCA. When an issue arises and the load angle curve start to rise, the system becomes unstable. The point at which the system stabilizes and the fault becomes evident, which is via the circuit breaker, is known as the key clearing angle. The temporary and permanent graph have the same principle. CCA creates instability in the system when an issue arises.
So in conclusion, power system stability is crucial for managing various disturbances like sudden load changes, making it a key research area. Simulation using MATLAB Simulink analyze power system behavior, focusing on rotor angle and generator speed over time. So particularly at bus 9, the report highlights the critical clearance time and angle, which is emphasizing the importance of stability in power system, especially in recovering from disruptions and maintaining synchronism. With modern power networks becoming more complex, stability is increasingly vital, with transient stability being crucial for managing severe disruptions. MATLAB's use underscores its roles in addressing stability issues. So the future work could enhance the stability through advanced modeling, real-time monitoring, and renewable energy integrations and grid modernizations, which is ensuring reliability amidst evolving challenges.